Good day, everyone. Today we're going to discuss the axiom of continuity. This is in continuation of the discussion of Hilbert's axiom. Okay, to start, we have here measurement problems. So there are actually fundamental questions. Um, this discussion introduces the deepest fundamental issues in geometry, the connection between the discrete geometry constructions and the continuous nature of mathematical space, revealing gaps that persisted from ancient Greece until Hilbert's work. So, what are the fundamental questions? The first one is we have, okay, we have how do we know geometric construction works? Okay, so this is a construction problem, no? Okay, so when we draw two circles with appropriate radii, do they always intersect? Okay, so that's the question. Um, Aside from that, when we construct a perpendicular bisector of a segment, does this midpoint always exist? And then when we trisect uh, an angle using compass and straight edge, are we guaranteed to find the trisection points? So why this isn't obvious? So every geometric construction assumes that certain points exist where lines and circle intersect. But what guarantees this intersection point actually exist? So without continuity axiom, there would be gaps in geometric space where expected intersection fail to occur. Okay. Aside from that, when when do two circles intersect? Okay. So the um this is the circle intersection problem. So visually, two circles seem to intersect when they overlap appropriately. But how can we how do we define overlap rigorously? So what guarantees that the intersection points actually exist? Okay. So there is the what we call as the mathematical precision needed. So for example, just for example, if we are going to consider two circles, one circle centered at, let's say, 0 0 with radius 3, another centered at 4 0 with radius 2. So these circles would intersect um, because the distance between the centers is less than the sum of the radii, but greater than their difference. But proving the intersection points uh, exist requires continuity axioms. Okay, the last one. Okay, how do we connect geometry to real numbers? So this is foundational connections. So coordinate geometry assigns real number or real number pairs to geometric points, but this requires that the geometric space has the same completeness properties as real numbers. So without this connection, coordinate methods becomes unreliable. So we want geometry and algebra to work together seamlessly. So when we say point P has the coordinate of, let's say, pi squared of 2, we're assuming geometric space can accommodate irrational number coordinates. So this assumption needs mathematical justification. Okay. If you can still recall with our first discussion, um, Greeks actually discovered the irrational numbers, the square root of two, because this is the diagonal, the length of the diagonal line of a square with side length of one. Okay, so there is a fundamental contradiction here because Greeks avoided irrational numbers in their reasoning, but their own geometric construction inevitably created irrational numbers. Okay, so as what I mentioned, the diagonal of the unit square has length of square root of 2, but they had no rigorous way to handle within the geometric systems. So, what are the other contradictions aside from the unit square diagonal? We do also have the golden ratio. Di ba? When you if you can still recall, the golden ratio is you have 1 plus square root of 5 all over 2. Okay. And aside from that, we do have the circle circumference, which involves pi. Okay. So Hilbert realized that geometry and real number system must have compatible completeness properties. So the geometric space can't have holes where real number exist, and real numbers can't have gaps where the geometric construction expect to find points. So there are what they call this one two crucial axioms. Okay. Uh, Okay. So the first one is the Archimedes axioms ensures no infinitesimal segments connects to Archimedean properties of reals. So when we say infinitesimal, meaning infinite, many, okay, uncountable. Infinite, in this infinitesimal, very or uncountable, very small, what we call this one, length. Okay. So another crucial axiom is the Didikins axiom ensures no gaps in lines, which connects to Didikins completeness of real. Okay. Archimedes axiom. If CD is any segment, A any point, and R any ray with vertex A, then for every point B not equal to A, on R there is a number n such that when CD is laid off n times on R starting at a point E is reached such that A is between B and E. Okay, so this axiom addresses one of the most subtle yet crucial aspect of geometric measurement. So ensuring that geometric space behaves like the real number system with respect to size comparisons and measurement processes. So if we are going to dissect, okay, this statement, okay, so you have here, um, if CD is any segment, A is any point, and R any ray where vertex A. So this is universal setup. So it works with uh, works for any segments, any starting point, and any direction. So there is no size restrictions. So the segment CD can be arbitrarily small or large. And aside from that, there is geometric generality. So it applies to all configurations in the plane. Okay. Another. then for every point B not equal to A on R. So there is now target specifications. So B is any point on R except the starting point A. Okay, so there is now distance consideration. So B could be very close to A or very far from A. Aside from that, there is universal quantification. So this must work for every possible point B. Okay, then you have there is a number n such that when CD is laid off n times on R starting at A. So there is now finite repetition. So uses only a finite number n of copies. So aside from that, there is now a construction process. Repeatedly place segment CD end to end along ray R. So the starting point, so we begin the construction at point A. Okay. And then a point E is reached such that A is between BA. So there is now surpassing condition. So point E lies beyond B when viewed from A. So there is now betweenness relationship. So B falls between A and E on the ray. Okay, so there is achievement guaranteed. We can always step past, okay, any target point. So as you can see here, we have the intuitive meaning, the stepping off principle. So you can imagine, okay, um, you have a very small ruler, let's say 1 millimeter long. So I claim that no matter how far I place a target point, you can always reach past. Uh, you can reach past it by laying. Okay, so just for demonstration, no? Okay, so even if the target is 100 meters away, you can get there. So 100 meters is equivalent to 100,000 millimeters, meaning there is 100,000 steps in your tiny ruler. So this one, okay, targets or rules out infinitesimal segment in geometry. Okay, so the key insight here is no segment is so small that it can't eventually add up to surpass any given distance. So this rules out segments that are infinitesimally small. So segments so tiny that they could never accumulate to meaningful distances. Okay. So um when we say this rules out infinitesimal segments, okay, take note that in the infinitesimal problem, in some mathematical systems, there exist infinitesimally small quantities. These infinitesimal are smaller than any positive real numbers, but still larger than zero. So if geometry contains infinitesimal, measurements could become problematic. So why infinitesimal break measurements? So if segment CD were infinitesimal, then no matter how many times you laid off, uh, you never reach any normal distance. So let's say a billion infinitesimal would still be infinitesimal. This would make measurement impossible. Okay, so Didikins axiom. So we have here, okay, suppose that the set L of all points on line L, is the disjoint union of the summation of line L, summation of points of the lines. You have line 1, line 2 of two non-empty sets, non-empty subsets such that no point on either subset is between 2 points of the other. Then there exists a unique point O on L such that one of the subsets is equal to the ray with vertex O and the other subset is equal to the complement. Okay, so this axiom presents the most mathematically sophisticated action in Hilbert system. So one that ensures geometric space has the same completeness properties as the real number system. So this eliminates any possibility of gaps or holes in geometric lines. So if we are going to bisect this axiom, so you have here suppose that the set L, okay, of all points on line L. So there is now a complete line consideration. So we're examining every single point on some line L. And then aside from that, we do have this uh, concept that we are treating the line as one set of points. So there is now a universal scope. So this applies to any line in the geometric plane. Aside from that, we have here is the disjoint union of the summation 1 union to summation 2 of two non-empty subsets. Okay. So there is now the what we call as the partition concept. So every point on the line belongs to exactly one of two groups. So when there is a disjoint, so no point belong to both uh, line 1 and line 2. Okay, the summation 1, summation 2. Okay. So union meaning together. So you there is the line 1 and line 2 account for every point on the line. So non-empty both subset contains at least one point. Okay. So such that where such that no either subset is between 2 points of the other. So there is now separation condition. So this is crucial requirement that makes this a cut. So no interleaving, meaning points from line 1 don't appear in the middle of points from line 2. So there is order preservation. So the subset respects the linear ordering of the line. And then you have here, then there exists a unique point O on L. Okay, so existence guarantee. So there is always such a point O. And then it's not just only existence guaranteed. We have uniqueness. There is exactly one such point O. And then point O lies on the same line L. Okay. And then you have here such that uh, one of the subsets is equal to the ray with vertex O and the other subset is equal to the complement. So one subset forms a ray starting at O. So there is a complement structure. The other subset is everything else on the line. So again, there is a complete characterization. So this describes all possible cuts of the line. Okay. Now, when we say cut or the cut concept, so imagine you have a line and you want to cut it into two pieces. So there are many ways to do this. So cut a specific point. Okay. The point belongs to one piece or the other, and then remove a point entirely. So creating a gap of the line. So the Didikens axiom, okay, says that every valid cut of what you call this one type 2, okay, um actually corresponds to a cut of type 1. There's always a specific point that determines the cut, and there are never any gaps. So there is no gap guarantee. Okay, so this axiom ensures that geometric lines are complete. They have no missing points. So everywhere you expect a point to exist. So based on ordering of nearby points. So there's actually uh there's actually is a point. Okay. Yun siya. So what this Didikins axiom established. So we have line completeness no hole. Okay. So every Didikins cut of a line corresponds to a unique point on that line. So no cuts create equal gaps or actual gaps rather in the line. So lines behave like a complete real number or complete real number line. So in some mathematical systems, you could have lines with holes, places where the point should exist but doesn't. So this axiom rules out such pathological cases. So every geometric line is a complete as real number line. Okay, another corresponds with real numbers. Okay, so each point on a geometric line can be assigned a unique real number coordinate. So each real number corresponds to a unique point on the line. So this correspondence preserves all ordering and distance relationship. So this axiom justifies coordinate geometry. So when we assign coordinates, let's say xy, to geometric points, we're assuming that geometric space has the same completeness properties as real numbers. So this axiom provides that guarantee. Okay. Another basis for coordinate geometry. So um fundamental uh, not fundamental foundational. Okay, fundamental importance. So this enables rigorous development of analytic geometry. This justifies calculus applications on geometric problems. So aside from that, it provides foundation for modern mathematical analysis. Okay, so there is a connection to real number. So um, this what I call this one? This is exactly Didikins' construction of real numbers applied to geometry. So just to go back, no, to the history. Okay, so as what I've mentioned, this action is based on Didikins, Richard Didikins. Okay, this is in 1858. Okay, construction of real numbers. Okay, so Dedekind showed that real numbers can be defined as cuts in the rational system. So partitions that either have a largest element on one side or smallest elements on the other side. Okay, so what do you call this one? So again, you have a real number. Okay, define real numbers as gaps between rational, and then every gap corresponds to a geometric point. And no systems have both system brothers have no missing elements. Okay. So application. So this what I call this one, the application of Hilbert's continuity axiom, showing how abstract completeness principle enables concrete geometric existence proof that were impossible under Euclid's system. So you have here uh, elementary continuity principle. So this is one of the two continuity principle. So if one endpoint of the segment is inside the circle and the other outside, then the segment intersect the circle. So um technically um we as we can say, no, visually obvious, okay, but requires rigorous justification. So this depends on the completeness of geometric space And take note, in the geometric space, no gaps. You cannot this cannot be proven from incidence, betweenness, or um, congruence action alone. Okay, so um, this uses Didikens' axiom to guarantee intersection points exist. So this eliminates possibility that segments jumps over the circle through a gap. So this provides a rigorous foundation for intermediate value theorem in geometry. Okay, so circular continuity principle. So if a circle gamma has one point inside and one point outside circle, another circle gamma prime, then the two circles intersect in 2 points. Okay, so this combines elementary continuity principle with circle geometry. So this ensures that expected circles intersections actually exist. So the foundation for all compass and straight edge construction involving circles. Okay. So why 2 points? Okay. So when circle intersects under these conditions, they typically intersect in exactly 2 points unless they are tangent. So the principle guarantees both intersection points exist. So this enables proof of, okay, first one, existence of perpendicular bisector. So given, let's say, given segment AB, construct perpendicular bisector. Okay. So um, what do you call this one? Without continuity axiom, the what do you call this one? Diba? If you can still recall with your grade 7, if you're going to construct a perpendicular bisector, you're going to form a line. Let's say that line A, segment AB, and then you are going to using your compass, you're going to uh, ensure that the opening of the compass should be one half of the greater than one half of the line that you are created, but less than the entire line that you have created. And then you are going to form an arc above the line, and then another with the same opening, you're going to move the compass to the other endpoint of that segment, and then you are going to create another what we call this one, another arc, okay, above the line segment, and then you're going to connect the intersection to the what we call this one, to the um line segment. Okay. Then you have now your what do you call this one? Your uh, perpendicular bisector. So without continuity axiom, okay, the arcs the arcs that have been mentioned a while ago miss each other even when they should intersect. So the circular continuity principle guarantees the intersection points exist. Okay. Another, you have circle-circle intersection. So two circles intersect when distance between centers is less than the sum of radii but greater than the difference of the radii. So continuity action guarantees intersection points actually exist. So this enables all construction involving circle intersections. Another is the existence of equilateral triangles. Okay, so the when you can still remember with your grade 7, you can construct, no, you can construct um equilateral triangle by drawing, okay, circle centered at, let's say, A with radius AB, and then another you can draw circle center at AB, center at B rather, with radius AB. So circle intersect at point C. by circular continuity principle, and then you can now have triangle ABC, which is equilateral triangle. Okay, so Euclid assumed the circle intersect, but couldn't prove it. So our continuity action provides the missing justification. Okay, another many classical constructions. So example for that, um, which uh, they have now rigorous foundations. We have the angle bisector construction, perpendicular from the point to a line, regular polygon construction, and the golden ratio construction. Okay, so isosceles triangle. So proposition, if triangle ABC, we have uh, segment AB congruent to segment AC, then angle B is congruent to angle C. So if you can still recall, with the we if we are going to prove the what we call this one, the base angles of isosceles triangles are congruent, we are going to form what we call this one, um, an angle bisector, okay, to the vertex. Okay, from the you are going to construct a not perpendicular, angle bisector to the vertex of that triangle. Okay, so again, this axiom, okay, ensures that we can have, or we can construct a angle bisect or an angle bisector rather. So um, if you have a construction of an angle bisector, okay, so since what we call this one, AB is congruent to AC, it's already given. Um, and then if you're going to construct uh, angle bisector to angle A, so again, it ensures we can ensure that there is really existing angle bisector because of the axiom of completeness, okay, or continuity. So if there is angle bisector, then that angle divides divides two congruent angles. So we have AB congruent to AC, so one side, and then uh, the angle the angle bisector. So we have two congruent angles, and then reflexive. So from that we can now have the SAS, and then from the SAS we could have angle B congruent to angle C because corresponding parts of congruent triangles are congruent. Okay, so that is the axiom of continuity. Thank you very much.